So as I said, today we're going to be going over machine learning, specifically feature selection, feature importance, and we're going to be talking a lot about SHAP values, which is a really neat area, I think, where analysts and data scientists can meet in the middle, as well as just being able to explain black box models to stakeholders who might not otherwise be able to understand what's going on. If you are not asking a question, please mute. I'm in full screen, so can't get off. Thank you. All right. So just a little bit about the data for those of you who are joining for the first time. This class uses the treatment episode data set, which is a very large data set that has every admission to a substance abuse treatment facility that is publicly funded by the government. So what we're trying to predict in our models are which admissions are first-time admissions versus those that were repeat admissions. The idea would be to be able to predict with a high level of accuracy those who are at high risk of relapse from substance abuse disorders. So that's what I'll be using today. I do provide a small sample of the data set, which is what we're going to be using today from a computing power perspective. I provide the larger one, but I suggest using the smaller one. So today we're going to be talking about measuring feature importance. As I go, please feel free to unmute and ask any questions. I can't see the chat right now because I'm in full screen. So please unmute, or if somebody's shy, feel free to read the question off to me. So what is feature importance? So feature importance measures the contribution of each feature or variable, if you've never heard that term before, to the final prediction in your models. Feature importance, when it is higher, means that a feature or a variable has a higher influence on a prediction and explains more of that prediction. There's multiple ways to measure this, some better than others. Today, I'm going to cover SHAP values, or Shapley additive explainers. That I would call the gold standard for feature importance. And then the secondary one that I use particularly with big data is tree-based model feature importance. Shapley values take forever to run, and they only work on smaller data sets, and there's not a good package that has a parallelized Shapley value function that I've found so far. So a little bit of background on the difference between global versus local feature importance. SHAP allows you to do something really neat where you can actually look at on an individual basis for every person in your data set, which feature it contributed to the prediction that they got. So it's a really neat feature that really I've only found SHAP that does that. So that's on an individual basis. So if you say have 100,000 observations in your data set, you would have 100,000 feature importances. Global feature importance actually talks about your entire data set. Often it's a mean of the feature importances for all of your data points, but it can also be something that's built with the model. The second thing that we're going over, generally is like a mean or an average of the different feature importances over each individual or row in your data set. So I show an example here. We're going to dig much more into these particular images down the line in this presentation, but the top one shows a local feature importance. So for this individual, the prediction was 0.306. This is a yes or no data set, predicts 0 or 1. So that would predict as a 0, that it was not a repeat admission. And it goes through and it shows the contribution of each variable to that 0.306 prediction. We'll go over that one in a lot more detail in a second. The second one shows global feature importance. So the feature importance across your entire data set. And that gives you a bird's eye view on what really predicts whether something happens or not. So now I'm going to go into SHAP values, and then I'm really excited to show some of the visualizations that you can create with SHAP values, because that's really, it's very useful for modeling, but it's even more useful for explaining models. So very excited to show that. So as we talked about earlier, these are called Shapley additive explainers. If you hear SHAP values, that's what I'm talking about. That's normally what we would hear. We'd either hear Shapley values or SHAP values. It is a model agnostic method for calculating feature importance, meaning whether you're using a k-nearest neighbors or gradient boosted trees or random forest, you can use this particular method across all of them. So if you're doing model training and you use 5 different types of machine learning algorithms, you can compare apples to apples in this case and use it across those. It is superior to regression coefficients. I wanted to mention this because this highlights the difference. Regression coefficients are different from SHAP value feature importances because they depend on the magnitude of the data. So automatically, even if it's less important, median household income will probably have a smaller coefficient for than something that would be, say, percent below the poverty line, just because one is a lot bigger than the other. So one thing to keep in mind is that SHAP values cannot determine causality. So just like any other prediction model, we can't tell what causes what, chicken or the egg problem, but it can give you more idea of what is contributing or associated with that prediction. So there are several types of SHAP values: the model agnostic, tree-based, linear, and neural networks. We're going to go over the model agnostic one today. The reasons why you would want to use the tree-based, linear, or neural networks is they work faster for specific types of models. This is a highly processing intensive method, so if there's a shortcut, you probably want to take it. And for anything tree-based, you could use that. Linear regression, logistic regression, use the linear, and then neural networks for deep learning. I'm going to stop. Are there any questions before I move on? All right. So I was looking through on ways to explain this, and I came across and adapted this example, and it really helped me understand exactly what SHAP values were and how they worked. So this is putting data analysis aside. This class is going to be more on the concepts, some about the code, but mostly about the concepts. So pretend that you're going out with 3 friends and you share wine, fries, and pie. So you're all eating from the same plates, probably not during COVID, but we want to know basically who should pay more than the other person, because everybody is eating, some people are eating more than others. So this would be a very roundabout way to do it, but it explains the concepts of SHAP values. So for SHAP values, you can pretend you have 3 people: Robert, Alex, and Paul. And we're going to go through a couple combinations to figure out what the marginal contribution to the total $90 bill would be of each individual person. So what that means will be shown by this example. So if Robert eats alone, he's going to spend $80. If Alex eats alone, he's going to spend $56. And if Paul eats alone, he's going to spend $70. So after we look at everybody alone, now we start looking at the combination of the people. So if Robert and Alex eat together, it's going to be $80. If Robert and Paul eat together, it's going to be $85. And then if Alex and Paul eat together, $72. And finally, if all 3 eat together, it's going to be $90. So now that we've used every single combination of those 3 people and played out as every permutation of that situation, we can actually look at the marginal contribution of each. So looking at them in order, because order matters here. So drawing your attention down to the bullet points. So an example of this, so if Robert was there, and then if we added Alex to Robert, Robert's already going to do $80, and Alex would actually have 56. So if Alex was added to the party, he would add $0. So if we added Paul to the party, he would contribute an extra 10, so to get you to that 90. Then if you go and look at Alex, who's 56, so you added Robert to the party, looking at his contribution, if you look at Robert and Alex together, it would be 80. So it was an additional $24 to add on Robert. And then looking at all three alone, when you add Paul, it was an additional 10. So you basically look at when somebody's added, how many additional dollars are added in by that one person. And finally, coming down to the bottom, all SHAP values are all the permutations in order and how much in each of those situations, in this case, a person added to the bill. So looking down here, so Robert added 80 here. It's Robert added 24 here, so 24. Robert added 18 here, 15 here, and then he added 18, and then finally 80. So if you find an average of all of those, his marginal contribution on average was $39.20. And we would repeat that process for all three people. And then you'll notice that for all three of the people, it will add up to, within rounding error, to about $90. So when you look at in putting this to SHAP values, it will be, instead of people, it'll be variables contributing to the prediction. And then if you look at the importance of all of your features, they're going to add up to the actual prediction for that individual person every single time. So if coming back, I'll show an example in the next one actually. So that additional SHAP value is the marginal contribution, and this slide shows outside of the math exactly what that means. Are there any questions about this? So giving full credit, the source for this particular example, the link is shown at the bottom. So a detailed explanation about SHAP values, bringing it back to the machine learning, the math. So say we get the SHAP value of an X feature, and this X feature will say age. We retrieve all the combinations of the remaining features after X is removed. So we removed X. We have all the remaining features, and just like the people, we find all the combinations between the features. So it'll be 1 in some cases, or 5 or 10, depending on how many features you have. It computes the effect on the predictions of adding X back to the group or back to the party in the case of the past slide. So sees how it changes and how that prediction goes up when that feature is added. And then features, those features are removed and replaced with those different permutations of all the features. And then we find the average value across all of the different data sets we looked at. And then when we aggregate it together with that average, that gives us the marginal contribution of the feature. One thing to keep in mind is the model is not retrained or redone for every combination of the features. It actually replaces, if a feature is taken out or removed, it replaces that feature with the average across the entire feature. So it's making everybody the same. Even so, as you can imagine, if you have 50 features in your data set, I don't even know how many permutations that is, but it's a lot. So you can imagine how long this often takes to actually go through this with larger machine learning models. Any questions about the last slide and how it compares to this explanation?
Yeah, can you using that eating out as a way to explain X and yeah.
Did you have a question?
I'm just saying I try to understand what is X.
X is a feature in the data set. So like I'm saying feature X or the feature in your data set. Maybe if I move on to the next slide and show a real example, that'll help. So in this case, this is one of the visualizations that comes out of SHAP. Shown here, it does get cut off, and in the actual package, you can, as you hover over the things, you can see them. So I can show that in a minute, the whole thing. But we can concentrate on the middle here. So this is an example of a local feature importance. So this is one individual in our data set. So now let's start with the base value. So for every observation, we start with the average prediction across our entire data set. So that's like our starting point for everybody. And that is shown, you can see base value. I don't think my mouse is shown in full screen, so I'm going to come out just so I can point to what's going on here. So our base value is here, where my mouse is showing. So this across our entire data set, our average prediction is 0.6451. So now, as our starting point, we want to talk about basically the contribution of each feature and how it increased or decreased it from that base value. So the red areas show the features that made the output value higher than the base value. The ones that are blue show those that made it lower than the base value. So everything here increased the probability that someone had a repeat admission. So everything shown in blue, it meant that they had a lesser risk of a repeat admission. One that makes clear sense here is, so this individual, it basically records when they come in what drugs they have in their system. And this individual did not have heroin in their system. Because they did not have heroin, that means that it decreased the risk of relapse. The risk went down. So that's something that is pretty intuitive. Another thing that we're seeing here, the Mid-Atlantic division. So if somebody lives in the Mid-Atlantic division, that's the census division, that's actually increasing their likelihood of having that repeat admission, so having come back. And then if we take all of the features and their contributions, these are the ones that increase, these are decreasing, and then it all adds up to the prediction that we actually got in this case, which was 0.87. So this individual was predicted to have relapsed in this case. So and what is shown here is for that individual, which features contributed to the prediction. It may be different, and these may have interacted differently if it was somebody else shown here. But this individual, this is how the breakdown was. Did that help answer your question about the features?
So basically, the base value is the average first, and then you're adding each individual one to it, and then yes. And then the prediction moves up and down, right? Some moves up, some down, and then once all the features get applied to it, and the end value, which is 0.87. So what's the threshold?
So
it bigger than certain number, and then it becomes yes, and if less than certain number, become a no.
Yes, so that is something to keep in mind here. So in this particular model, it's imbalanced. So there are more people that weren't repeat admissions than those that were. So the threshold in the model, generally the default is 0.5. In this particular model, the one that performed best was 0.6. So the threshold is set there for this particular model. So it would have been somewhere around here in the middle. All right, that was a great explanation.
So Kelsey, can you go to the previous slide, please?
Mm-hmm.
So does this mean that, let's say, if I have 50 features, so I will have like how many, 50 factorial experiments or something to get this? So we first take the average on the, let's say, first one, then the other 49 is there.
Yes.
Then we add it, then we remove one by one the other ones. So that's quite expensive, right? That's like the...
Exactly. Yes. So that's why in this class, I'm teaching the gold standard and then a second best way. That's a lot quicker. If you have any more than 500,000 rows, you probably can't use this. And even in this particular case, I used a subset of the data that was randomly chosen, 200,000 rows, and I had to actually take the SHAP values and randomly choose 10,000 to show today. Like it's very, very expensive. You're right, but you're explaining it exactly right. But you can see why I'm giving two options for feature importance. This and then something that's close to as good, but not quite.
Kelsey, two things. One, how many rows did you just say?
In this particular model,
what your kind of guidance is for SHAP.
I would say anything over 500,000 and don't even try it.
Second, there's a question in the chat. Conceptually, is this how dropout works in neural networks?
So dropout, it would be a different thing. Yeah. So this is just a measuring of feature importance. Any other questions? So yeah, extremely expensive. So I did 10,000 rows. I subsetted it to show these particular images. And I think it still took 20 minutes. So and there were probably, I think, like 50 features in this particular model. I'd have to look, but it takes a really, really long time.
So you think it would be better if we look at the feature importance starting from the highest value of importance and ignore those features as lower feature importance?
There's a fine line there. So that's where it starts to, there isn't really a good answer to that question. So I'm going to go over at the end of this, my process as a data scientist on how I would actually draw that line. And I'm going to go through some code and actually show, okay, this is how I decided to stop. So this is basically telling us how, and I'm going to go over the process of feature selection. It's probably the thing that my newer people have the most trouble with that I've taught at jobs, is knowing what to do based on these importances. So we'll definitely go over that. So just a little bit more on the visuals, and then we'll get to the process and how it works in practice as a data scientist on the job. So this individual, it's shown here. I believe these are the same people. Yes, they are. And I'm just going to zoom in so you guys can see this a lot more clearly. So this top one is called a waterfall chart. So this one is really good. This would make intuitive sense to a stakeholder who didn't understand machine learning. So for this person, again, we're looking at that person who had 0.868 as their prediction. So they have mental illness. So that added 0.05 to the prediction on average. They came to the center through ambulatory services, so through an ambulance. That added 0.05. They had cocaine in their system, so that added another 0.05. And going down, they did not have heroin in their system, you'll remember. So that decreased it by 0.02. The first use, they started drugs later in life. So that meant that it went down by 0.02. I'm reading the question. Is it possible to group similar features together to help the selection process? We'll go more over the feature selection in a minute. So that'll be down farther in the presentation. I want you guys to understand what SHAP can do and the other way to do it, and then we'll talk through the selection process. So another way to show this particular example is through a decision plot. So we basically are starting from our prediction up here and looking had the impact that it had. So if you start down here, this is the average value. They had alcohol in their system, it looks like, so it went up. They were a gender that their gender made it go down, so on and so forth. So you can see here, the first use made it go down, and then the heroin made it go down, and then it went back up because of all of these features. So basically, you can see its path here versus more broken down over here. Another cool one to look at, and I've actually just recently used this pretty heavily on one of my analyses. So this plots all of the 10,000 random rows that I calculated SHAP values for. It's the ones that are red are showing that they have high values, and the ones that are low have low values. And then it's showing the SHAP values themselves and where they hit based on this lower axis here. So in this case, one of the most important features was being from the Pacific region. So if they were in the Pacific division, that meant to a varying degree, depending on who the person is, if it was higher, this was a 0-1 variable. If it was 0, that had a negative impact on the prediction, so it went down. And the impact for each individual varied based on who they were. And I'll have an interaction in showing how that works in a plot in a couple slides. And then you can see the impact and maybe who would be an outlier and who was affected by these most and who was affected by them least. And you can see that some of them are spread out and some of them are close together. So some of them are having a higher impact than others. Any questions about that example? All right. Now this one is global feature importance. So it's showing an average across all of the SHAP values across the 10,000 random rows that I picked, the marginal effect of each variable. So heroin is the most predictive of relapse. And notice here that there's no positive and negative. So this is the absolute value of the average. So it's the importance, whether it's positive or negative. So this is basically taking importance, whether positive or negative. So that's something to keep in mind. So heroin had one of the bigger impacts, and we remember from the past slide that it made it go up. The division Pacific was the second most important, and it in general made it go down. And I believe South Atlantic in general makes it go up, and so on and so forth. So you can see these, and this is what you use for feature selection. So you'll see me go through that process in my code. But this is what you would leverage in order to make those decisions on feature selection, something like this. Any questions? And then this one is great for identifying bias in your model. So as you're a machine learning, you probably hear in the news periodically that somebody created some facial recognition software or something similar that was biased towards one group of the population. It's usually because they don't sample enough people of the subgroups in order to get an accurate prediction on them. That's usually what it causes it. So you can actually say, if you wanted to look for bias in a certain gender, you could do a plot like this for males versus females and see what the feature importance and how it differed by gender. Right now, I'm showing some, if it doesn't have lines in it, it means these people do not have mental illness. And if they have the lines in it or the lower bars, it means they have mental illness. So for instance, the interesting one is the division being in the Pacific region. It makes more of a difference if they do not have mental illness. If they do have mental illness, then it makes less of an impact, which makes sense because mental illness often contributes to substance abuse. So that one feature is going to outweigh where you're located in the country if you're looking at one feature versus another. So this would be great for bias, and you always need to check that on your models or you're putting your company at risk. So that's something, always push that. When you make a model, say we need to track the different groups of people and we need to make sure that the accuracy is similar across groups and that we aren't biasing based on some specific feature that is out of the person's control. So always keep that in mind, and it's best to automate that process and keep the records and keep the metadata from this process. So if somebody comes and audits you, somebody comes and said your model is biased, you will have that and say, actually, we checked for that. And it is lower because of XYZ reasons, and it was not that my model was inaccurate for this group of people. So always keep that in mind to protect your company with that. Shown here is age group. I'm gonna go in a little bit more. So age group shown here, in this case, it was a recoded age group because that's how the data set came. So I put a little key here. But basically, and this is looking at the interaction between heroin and when they first used the drug. So shown down here is first use of the drug. The color is whether they use heroin or not. So in this case, we can see that if they used a drug at 0 or 1, so below 18 years of age, that in all those cases, it contributed or increased the likelihood of relapse. If you're between 18 and 20, it's kind of split. Now, if you do it from 21 up and to the end of the life, so anyone above 21, it decreased the likelihood of relapse. And then you can look at the impact of heroin, then how it interacts with this particular variable. So whether if they did heroin when they were young, heroin, using that wasn't really that important. It was that they were using it so young that was most important, that influenced the behavior. It's mixed when you look 18 to 20, it really doesn't seem to have an impact at all. And then consistently a 21 and over, the heroin use actually increases the likelihood of it being a readmission. So, and then you're starting to see it get a little more mixed at the last age group, or 30 years and older. So this is showing how they interact with one another. Any questions about this or any previous slides? Right. So before we move on from the visualizations, this is something like at my old job, I used to work at Avanade. There was a machine learning competition, like a hackathon for a particular client. And everyone who came to the table got judged and they picked the best product. So all the models, there were some models that were better than the one that won, that were more accurate, but the one that won used a dashboard and made it with SHAP values. And the reason that they won, the client told them, was 100% because SHAP values made it easier for them to understand and made it more explainable. So that's how you can leverage this on the job for people. You can understand the marginal contribution. It's easy to say the contribution of one feature was this and explain that. And also there's a lot of cases where you can hover over these and look at each individual one by one in an interactive dashboard. So it could be really, really useful for explainable AI, especially in dashboards. So I'm going to jump real quick to my code, so I can show a little bit of what the code looks like and how SHAP values are done. So in this, I'm going to go over feature selection last, but showing real quickly how these plots are actually made. So in this ended up being the best model. I automatically picked it and did automated feature selection in this case. So this was my final model. Remember, we're using a very small portion of the data. So this would probably be better if we use the extra million observations that were available to us, but I wanted to make it so your computer could actually run it. But it was 0.71 was the accuracy. And you can see the F-score for 0 is 0.66 and the F-score for 1 is 0.74. So it's basically identifying the ones better than the zeros in this case. But down here, you'll see in this particular case, we wanted to look at this model, and I made a function that allowed us to look at the predicted probability. And when you look at the predicted probability, it usually gives you both the probability for 0 and 1. So this allows me to pick the last one. So the probability of getting a 1 in this case. In order to do any of these visualizations, you have to use the explainer package, or the explainer function from the SHAP package. And this will be available in R as well if you're an R user. It works just the same way. It might look a little different, but under the hood, it's the same. So in this case, it's taking and finding that predicted probability, taking our training data, and then this just gives it the feature names. And then in this case, I used 10,000 observations only in order to calculate these SHAP values because it just takes so long to do. And I didn't want to sit there for 3 hours to let it finish. So I did a random selection of that, which as long as you're randomly choosing, that's fine. So I was able to then take the actual SHAP values. Hopefully we can. I'm a little afraid to do this, to try to print it. Okay, I didn't know if my computer would explode if that happens. So it shows you the values and then the base values. So this is the average, and you can see it's the same across all the participants. And then the actual data that it came from. So the features that went into the calculation. That's what the SHAP data looks like. And you can take it, use those SHAP values to create these images. And they look very similar to what you see here, those functions. And jump back. Any questions before I move on? All right. So say you don't have unlimited computing resources and you're in a real life scenario where you can't use SHAP. I use this more often than I use SHAP. So tree-based model feature importance. If you've come to the class before, you've heard me talk about this. We went over gradient boosted trees and random forests in the last class. If you're interested to hear about that, it is posted. The last two classes were tree-based models. It's posted on my YouTube channel and on my website, kelseymnet.com. So tree-based models by design take and they train a bunch of tiny decision trees throughout. So it's usually hundreds or thousands of decision trees, and it uses subsets of your features for both of them. So by design, it's taking variables out and putting them back in, just like SHAP values did. It's not going to happen in as systematic of a manner because there's a lot of randomness to it in that case, whereas SHAP, not as much. And then using that, it can try to, it then finds the average of how the accuracy changed when you added or removed features. And that can give you a feature importance value. This basically allows you to do something that is inherent in the model itself versus actually something that you have to go out and write code to do. So it doesn't increase computing resources at all, and it takes a lot less time. So flipping real quickly to my code. So I'm going to go farther up towards the top. So this is an example of a feature importance. So the way I usually do this is I start off with everything. And then I start to winnow and chop things off. And I'll go more into that in a second. But shown here, the feature importances. You're seeing some commonalities here, but the order is different. So the same things are coming up, but they have a different importance. This tends to not be as accurate as SHAP, but it takes a lot less time through the process. Any questions about this before I actually go through the feature selection process and how that works?
So this list on your screen is the results of you running the SHAP classifier or tree based. Yeah, okay.
So it's the actual model.
Okay.
Yeah, gradient boosted classifier and gradient boosted regressors actually create feature importance without you asking them to. It's just something they do.
So for example, you talked about earlier how there were different ways on where you could pull out certain accuracy points. So would this be random trees be a good way for you to narrow down like a smaller number of variables for you to use in SHAP features? Do you use it for that often?
So I usually, because there's so many data points, even if you reduce the features, if your data set is big, SHAP's not going to work. So 90% of the time I end up using this for everything. So it just in general, it's the most computationally or least expensive way to do it.
So this list of the feature importance, actually you haven't touched the SHAP yet, just using the gradient boost classifier to fit the training data to get those importance that listed out.
So I think this might be the confusion. It's one or the other. You don't use both in the same scenario. So SHAP methods are the gold standard and the best way to do it if your data set is small enough. In real life, your data set's usually larger. So in most scenarios, you're going to end up just, I recommend using the gradient boosted trees or random forest alone. You can't really mix and match much because if your data set's big enough, you can't use SHAP at all. But if your data set's small enough, you'll want to use SHAP because it's better. It does the job better. So it's really, whether you pick one or the other, it's data number of rows. And then you can't really mix and match when you do it. Does that help clear that up? I think they're two separate ways of doing or methods for doing the same thing.
Yes. So you're showing the tree-based model first, and then later you will show the SHAP method with a smaller set of data, I guess, to have a higher accuracy. That's what you will show later slides.
Yes. Well, I'll show you it in the code, actually.
Oh.
I'll show you how I did the whole, like how they differed and what the accuracy difference was and all of that. So just real quick as a recap, so SHAP methods are more accurate than the other way around. They also allow for calculation of local feature importance, which you cannot do with tree-based methods. And then they do have some additional methods that are faster. So for tree-based models, you can use the tree-based SHAP value and it will help make it more optimized. It has great visualizations, tree-based doesn't. And it allows for the detection of bias in machine learning, which the other one will not. The major con, like we said, it's highly processing intensive. Lime is an alternative to SHAP. I've never used it, but it's apparently similar, but less intensive. So tree-based methods, the pros, it's not processing intensive. It's calculated automatically. You don't need extra code. It's not as accurate, and also it's less effective at removing highly correlated variables. So if you have median household income and percent below the poverty line, both in your model, it's going to be less effective at removing one of those. The highly correlated features can mess up your model. So feature selection. So what is it like in real life when I'm using and doing this in real life? There's a lot of nuance to it. So I'm going to warn you guys. So I get these questions a lot, but just as a review, overfitting is a big problem in machine learning. And usually when you're tuning it, you're trying to get the balance between underfitting and overfitting. And that's your most accurate model almost every time. What overfitting, it stems usually from having too many features or having something tuned in your model incorrectly. When it overfits, it memorizes the training data, which means it does not generalize well to unseen data and that you look at in the future, which is how you'll use the model. It gives this, I thought, was a very intuitive example. The regression being shown on top and then classification on the bottom. This is going to be more like our use case. So the underfitting in this case, it's drawing a straight line. It's not getting the classification very well. Here, it's doing a curve. It's getting it pretty well without being too complicated. And this would be an example of overfitting, memorizing the training data. And then this particular model would not generalize well to new data because it's not going to look like this. So feature selection helps reduce overfitting by removing features that are highly correlated with one another or just having too many. Model tuning can help with this too. So what does the process look like? And that's what these questions, a lot of them were about. So how do I use this feature importance thing? So feature selection is a process where you have to choose the most important features with either SHAP or tree-based model feature importance and avoiding that memorization. It's best practice to also remove highly correlated features. This often is informed by business knowledge. So I can't stress this more than you have to have a good understanding of the domain to do machine learning correctly. So always keep that in mind. And here's the example that I said earlier, 2 income measures, median household income and percent below the poverty line. They're going to be highly correlated with one another. And the goal is to find as few features as possible without allowing the model evaluation to suffer. How do we do this? So this is the process that I've used throughout my career, and it generally works pretty well. I usually do feature selection before I do model tuning. So I get rid of the extra stuff I don't need, and then I do the more fine-tuned tuning of hyperparameters like max depth, things like that. So first, measure the feature importance, whether it's with SHAP or with the feature importance from the tree-based models. I iteratively remove features while also keeping an eye on the F-score. I also keep an eye on precision and recall, because that goes to false negatives and false positives. In general, you're going to see the F-score drop somewhat as you take features out. And then I get to a certain cut point, and I'm going to go into the code and kind of show how I usually make that call. When the F-score drops past a certain level, I go back to the model where the F-score was the best, where I had whittled down the features enough, but still had an accurate model. And you want to use few features as possible without a drop in the F-score. So this is what the process would look like with SHAP values. It looks a little different for this would be for the tree-based models. I recommend running both gradient boosted trees and random forest when doing feature selection. The reason that I recommend this is both calculate feature importance slightly differently. So you're more likely to, if they are showing up as not important in both models, then you're more likely to be right. So if they're two highly correlated features, usually in one model or the other, one of them will get dropped. So it gives you a little bit more of a generalizable answer when we calculate it 2 different ways. And then in this case, I would export the feature importance. I would find the mean between the two is usually how I do that systematically. And then I continue the process that I described in the last slide. So now I'm going to show what it would look like in practice. So what I basically have in my code here, I have all of the data for the recoding available to you, but you don't need to run it. I have this intermediate spot where you can read in a small data set instead of the whole one. So if you're going to run this, you're going to want to start here. And then it goes through the process. All of this process of setting up models are in my previous class, but I'm going to focus on the feature selection. So first, I use the kitchen sink. The first model, I throw everything in all at once. And you never want to use this model in production, ever. It's bad practice, but the idea is to whittle it down. And I usually take off, depending on how many features, this can be a little bit. So for SHAP values, you're going to see as you take them out, it will gradually drop. With the feature importances from the tree-based models, you're going to see a drop-off effect almost every time. So showing here, this is done with the SHAP values. The SHAP means here, you're going to see if you go down this code, it's finding the mean SHAP values. We start off at 0.71. And then if we keep an eye on the F-score, it's 66 and 74. So we go down to the next one, 71, 66, 74. It hasn't dropped, which means I need to keep going. I need to keep removing features. In this case, I remove 5 at a time, I believe. If you have more features, you might want to do 8, but sometimes don't ever chop off all of the zeros. The reason for that is as you take out features, the feature importance above on the remaining features changes. Your order is going to change once you take off the really unimportant stuff. So I recommend, and I think that answers the question that we have here earlier, where I don't chop off all the unimportant ones. I take them off iteratively. So choose 5, 8, if you have a really small model, 3, and chop those off iteratively. And then in this case, I started with 65 here. So 65 produced this number. And then I come down, I did 55 in this case, I believe. Sorry, 60 hasn't moved. 55, 66, 74, 71 accuracy, still good. 66, 74, 71 accuracy, keep chopping off. 66, 74, 71, still going. And you're going to go through, now you're starting to see it go down a little bit. So now we're at 70 accuracy, 65, and 74. And we're sitting at 40 features in this particular case. So it dropped a little, but let's see how that changes and goes down. 65, 74, same as the one above. 65, 74. So something that you're seeing here with the SHAP values, it gradually goes down. So you're going to want to try to figure out what's the least amount of accuracy that I can handle. In this case, I actually believe I stopped it where the last one where it showed this 65 and 74. So kept that model in particular. You're going to see a more gradual drop off with SHAP because it does feature selection better than the other method. So going down, I think the last one I checked was, let's look for, so that's the first feature importance. So the last one I did was 20 features. And we're getting 64, 74, and the accuracy is 70. So it's still a pretty good model. So what I ended up going with is 45, because that's the last one where it had 71. There's not a great cut point here with this type of feature importance. So you can go up, they're very close. It's going to train faster with fewer features. I just picked the one before it dropped, but your models are pretty good no matter where you make the cut point there. Now, it's a little different with the feature selection with the tree-based models. Let me see. Is there a good method for finding overfitting if a problem? So the finding if overfitting is a problem, that's where the F score will, since I am basically testing with an out of sample piece of data, the F score is going to tell me that. So if you want to hear more about like the process of model validation, I believe that's my 3rd class. So I'll point you there to talk about overfitting. But we're basically tracking the accuracy in these cases. Well, F score, F1 score is what I recommend using. Yes, and having an extra holdout data set can help with that as well, which I go through in the validation part of my class. And then finally, for the feature selection, if you have to use the tree-based importance feature selection, you're going to see a drop-off effect on this one. So it starts off similar, 66, 71, go through. Now it went to 65, 74. So both of these dropped by 1. 65, 74, still doing okay. 65, 74, okay.
Kelsey, how many features are you selecting in these?
I'm doing 5 at a time.
Okay, it dropped immediately. Okay.
So yes, it dropped immediately, but you still wouldn't want to use that many features because that's a risk of overfitting. So I would still remove them. Even if it dropped a little bit in that case, you have to find the balance between the two. That's too many features in that case, in my opinion. But you're really going to see, so it starts to drop, drops a little, and then you can see it. It usually, I call it the tank effect. It's usually even more dramatic than this. Here it dropped basically, it was at 66 and 75. In most models, I see it go like that. It does really, really well until it doesn't. And then it tanks. But if you look at the feature importances in my final model down at the bottom, I actually do not think I printed those, unfortunately. So I will, I think I have an intermediate one in here somewhere. So the one thing I will say, okay, I think this was one of the closer to the ones that I chose. Even at the end, when you get to your final model, and I'm not sure if this one is the one that shows the final. It may not be. But you're going to see that some will have very small feature importances, and they're still in your model. That's counterintuitive to people who haven't done this before. But the thing about machine learning and the beauty of it, and why it's better than linear regression or logistic regression, is that the machine learning model can learn from very small, learn small pieces of information from these variables that aren't that important. And it basically weights certain variables more than others. So even if it looks non-important, that's why I do the iterative chop off. Example, I was doing a predicting for a dealership how much people would come and spend on services for an automotive client. Had my feature importances, I had 3 demographic variables at the bottom that had almost 0 feature importance. I took them out. The model, you wouldn't believe how much it tanked. And they were all close to 0. But when I took all 3 out at the same time, the model was destroyed. So always do it iteratively, like small chunks at a time, and you will get your best model that way. Any questions before we sign off? I know we're a little bit over. All right, I'm going to do one more shameless plug. You guys heard this. I'm going to stop the recording real quick. So we